A hungry, hungry black hole. So big, it's eating one of our suns a day. Exomoons, the next logical step in exoplanet discovery, have been identified in old Kepler data. And unlucky 13th for Rocket Labs, stumbling at the last hurdle in getting to orbit. It's Saturday, July 11, 2020. I'm Matt Miller, you're on Trekzone, and this is Talkin Science live and uncut.
With the latest science and space news 5 days a week across Apple Podcasts, Spotify, Google Podcasts and YouTube. This is Talkin Science with Dr. Brad Tucker and Matt Miller.
And it is a very happy Saturday to Dr. Brad Tucker. Brad, you spent Tuesday's introduction admonishing me for my brutally warm winters. How's today going for you?
Oh, look, it's warmer. The minimum was 3. So, it beats -5. So I guess that's a big change, but partially because of clouds and rain. So temperature like time is relative.
Bring on summer, bring on daylight savings.
See, I don't know if I want to bring on summer, though, after our last summer. I don't really know what I want anymore. I just want, neutrality. Neutrality, that's right.
Let's just all go hide somewhere in the desert. Of course, you can find Brad on social media, Dr. Brad Tucker on Facebook, btucker22 on Twitter. Trekzone's all over social media as well, Brad. Let's dive into the headlines.
Talking Science headlines.
And our first headline this week is the Mars Perseverance rover. It's been delayed again.
That's right. We've talked about that. It was originally gearing up for a 17th July launch, which means we'd be covering it in the show next week. However, that is not the case. It has been delayed twice, not both because of the instrument, but because of the rocket now aiming for a 30 July launch. So it's getting towards the end of the window, so they are running out of time, but they're still on track to launch in the allotted window in the next month.
And we'll be sure to cover all of the delays and the whole mission as a whole when it actually does get really close to launching or even when it's launched. But speaking of launches, we're going to find out more about Spaceship Two, Virgin Galactic's next space liner. They've got a bit of a YouTube event planned on July 28th.
That's right. It's been an important thing what it's exactly going to look like for this rocket or spaceship, and the cabin. So kind of what your accommodation or your travel style will be unveiled later this month. So it should be pretty exciting to see what $250,000 for a space holiday will get you.
Everything seems to be happening at the end of July.
Yeah, look, it's going to be a packed show. Let's just tell you, people.
Talking Science, stories of the week.
And Brad, as we do each and every week, 3 stories to fill up our show, fill up our goodness of science news and space news as well. And this one has me really, really worried. A black hole that's eating a sun a day. What have you done to me, Brad? Why have you given me nightmares?
Because it's 2020 and it's July, so...
Something has to happen.
Something has to happen. No, luckily this is not a disaster that we'll have anytime soon, maybe in 20 billion years. So this is a very massive black hole. So this black hole is 34 billion times the mass of our sun. So to put this in the scale, the supermassive black hole in our galaxy, what we call Sagittarius A star, is 4 million times the mass of our sun. This thing is 34 billion times the mass of our sun. And because it's so big, and the gravity and what we call the accretion disk, the gas and stars spinning around it, it's literally sucking in about a sun a day in terms of stuff.
Now there's some scale involved here. As you're saying, it's almost 30 billion times bigger than even the black hole of our galaxy. So the universe is huge.
That's right, exactly. And so this is really a monster black hole, and it's far away. It's 12 billion light years away, which is always good. You like it. You want a nice buffer zone between you and the monster black hole. But I think the really interesting thing here is one of the big studies or goals that we're trying to do is to figure out how big and how fast black holes can get. So essentially, how big can they grow? Now, as we look backwards in time, the universe is smaller, things are younger, takes more time for things to grow. So how do you get something that big that early?
And the black hole is called J2157. It was found, funnily enough, like you think of black holes and you think of against the inky blackness of space. How do these things get found? And this one was found by its really bright ultraviolet light. So we don't want to get close to it, aside from the fact we'll get sucked in, but we'll also get bombarded with UV radiation.
Exactly. And this is how we find it, is we find less of the black hole itself, but of the feeding frenzy. So, it's kind of like a dog, or especially a beagle. You don't see the food go into the mouth ever. You just see the evidence and the destruction left behind. And that's exactly what the black hole is. You don't want to see into it, but things go into it.
Now, if we had this monster sitting at the center of the Milky Way galaxy, it'd appear 10 times brighter than a full moon. Again, we're coming back to this scale. It's just incredible and really hard to fathom.
Look, it really is. And it just shows you the range and how powerful these things can get, especially black holes.
And I do wonder, is there enough material to keep feeding this monster? Or what's going to happen when it starts getting hungry?
We know black holes go through periods of feeding, essentially, that they feed more, they feed less. And it all depends on how much stuff is around and how quickly it can swallow it. Black holes do have a limit. So when we try and find these big black holes and what we call quasars, so very active galaxies dominated by a black hole, the question is how do they get that big that fast? And this one is really defying belief of how getting that big that fast when the universe was only 10% its age. And so that's the question, is how long can it keep this process up?
Alrighty, Brad, our next story of the week. I'm loving this one. Exomoons are now a thing. Not just now, but they've been posited, they've been possibly discovered, and now there's a few more candidates that have been discovered.
We've talked a lot about exoplanets and the planets being found and the diversity range from big Neptune things to Jupiter things to Earth-like things. And one of the big questions is always, we know how common planets are now. What about the moons? We see all of the moons in our solar system. What about exomoons, moons around those planets, around other stars? And a few have been hinted at in the past, and I think there's probably two that are fairly believed to be confirmed, but a new analysis of some of the interesting objects from the Kepler Space Telescope has found probably 6 potential new moons, so definitely boosting the pool of known exomoons.
It makes sense that there are moons out there orbiting other planets, really, doesn't it? Because one of the things that astronomers have been discovering is that our solar system really isn't that unique.
That's exactly right. When Kepler was launched 15 years ago, close to now, the main question was just how common planets are. We didn't know it at the time, and we only knew of a decent amount, but we didn't know the range of stars there around, how many, and that sort of things. When it discovered there's so many, and it is common, as you said, things like our solar system in terms of multi-planet systems and the types of planets are common, then it just kind of, everyone just made sense, like, yeah, there are moons out there. But the trick is, it's hard enough to find a small planet. It's really hard to find a moon around that planet. So you're not going to be able to find all of the moons. You're not going to be able to find the small moons. Things like Mars, not only is the planet hard to find, but the moon is essentially impossible to find because they're tiny. But you can find the things like our moon, or the bigger ones around Jupiter, Saturn, or Triton around Neptune.
And to use your needle in a haystack analogy from a few weeks ago, this is like finding a needle in a haystack here on Earth, but instead of being on Mars, you're probably on Pluto.
That's right. And you're trying to look through the eye of the needle at the same time, just to, because you have nothing else to do. And look, you're talking about very, very subtle problems and changes, because, the trick here is what you're looking at is the planet going around the star. And as it goes in front of the star, it blocks some of the light. It eclipses it. Now, what you're trying to do is firstly figure out how often it goes around so you can get an understanding of its period and its distance. But if there's multiple planets, that changes because they're at different distances. So those eclipsings happen at different times and different strengths. So how do you distinguish the multi-planets? So there's just multiple planets in that galaxy, or that star system rather, versus the moons going around it. So you have to kind of time it. So if you do think it's a moon relative going around the planet going around that star, you're going to only see the extra eclipsing of the moon when the planet is near the star, not always aligned, but pretty close to it. And you're looking for obviously very subtle variations in the light curve. And you need to have this happen multiple times to not only confirm it's real, but rule out other possibilities. So it's a really big trick to try and do this. And, you know, a big, remarkable piece of work to find 6 of them.
It is incredible. And thinking that most exoplanets are found using the transit method, as you've talked about, across the star, to think that then you've also got to look at the transiting object to see whether that's doing anything to find these moons. It's just incredible and puts into perspective just how much data is involved in these readings from Kepler. As we've talked about in the past, the project ended in 2018, and astronomers are still studying the data and still finding new stuff to talk about.
Yeah, it's a remarkable data set, and it's why it was such a big mission and changed our view, because it did all that, because of the precision, because of the work. And there'll be more discoveries, and as we find new things or new planets, we'll go back and look at the Kepler data to see if it was there, or, you know, as we discover new ways of finding out or distinguishing between moons and planets, we'll go and look at it, because TESS, as we've talked about, Kepler's kind of replacement, is monitoring some of the same things Kepler did. So we'll have a very long baseline of time, and that is an important thing. The general rule of thumb is you need at least 3 transits to confirm the planet at least. So, you know, if you're something like Jupiter, where you take 10 years to orbit the sun, or, you know, 7 years to orbit the sun, you have to wait 20 to 30 Earth years to see that. You have to wait a very long time. Even Earth, you have to wait 3 Earth years. Mars, you're talking about 5 Earth years to see it 3 times. So you really need to wait and, you know, play the perseverance game and the data collection game and the analysis. So, you know, over time, the rate of discoveries will even increase from what we found today.
And that's very similar to exoplanets, really, isn't it? The rate of discovery of exoplanets, it really has picked up in recent years. That's
right. You know, perfecting the techniques, the strategies, what we want to look at, where should we be looking at? It's really, you know, the sky's the limit, so to speak, pun intended here. And, you know, and that's kind of the remarkable thing. And, you know, one day we'll be able to, in the future, you know, not this decade, but, you know, look at and zoom in on those moons, just as we've had in our own solar system, to see what they're like, what could they contain, you know, are they similar to some of the very, you know, exotic and interesting moons of Jupiter and Saturn, or are they more boring ones like our moon, or God forbid, Mars's moons, which are just bleh.
They're just going to become a ring system again. Boring.
Exactly. It's going to be a ring system. Come on, you're just a failed moon here.
Well, we've talked about analyzing Kepler data, old data, and finding new things. Hubble still finding new things. One thing I've never actually asked you, Brad, is just how long after the mission is completed do we run out of things to learn in the data? You know,
this is a good question, because it's increasing with time, in the sense that as the mission's telescopes, or, you know, both on the ground and in space, get more complex or more interesting, the discoveries keep happening longer after. And, you know, and it's really about data volume. So some of the space telescopes, for instance, 20 years ago, they couldn't look as many things in many complex ways. So there's limited ways of reanalyzing it. For some things, if you just need pure data volume, so you just need to look at things for a lot of time over a long period, you'll keep reusing it and reusing it. And this is kind of the way, especially astronomy and space science, is going. There's just so much data pouring in from all the facilities that we have and all the different ways of measuring and observing and calculating, that, you know, some people don't even observe or collect new data, because there's just so much out there. You reanalyze with new objects or new findings or new studies or new ideas. And this is, I think, one of the very important part of the community is what we call open access, where just because you built it, make it freely and publicly available. Because, yeah, you want to do your science, but tens to hundreds of other people will have other ways of looking at it, analyzing it, and it just extends the richness and data of it. And that's part of it too, where in the past, if you took the image, say 30 years ago using photographic plates, or 40 years ago using photographic plates, and you took a little glass plate of that star or galaxy, only you pretty much just kept it in your office. No one else saw that. But nowadays it's so publicly available that everyone's like, oh, I've been trying to look for these things, or I was looking at that star and it's here as well. There's just so much way of overlapping that the science is becoming increasing and reusing old data because we're making it available to use old data. In fact, one of the projects I'm doing right now is digitizing our old photographic plates to link it with our database, the same database that listeners would have heard that big black hole was discovered, we just talked about, from, and finding ways of reanalyzing that. We just have to make it available.
Well, it certainly is future-proofing the industry and allowing many more astronomers and researchers to come up and study. If there are students listening and wondering what they're going to do with life, they have a fascination for astronomy. There certainly is no shortage of stuff to do as an astronomer.
That would be the fair statement of the century. Let's say that.
You can get social with Trekzone. Australia's unofficial home of Star Trek is everywhere you are. Just search for Trekzone.
Alrighty, Brad, our last story of the week for this week. ROCKETLABS, the California-based company, performed the most rapid turnaround between launches with its Electron satellite. Unfortunately, Flight 13 has proven to be a bit unlucky.
Yeah, look, it was heartbreaking over the weekend to see, as you said, they had the quick turnaround. They actually moved up the launch window a tad because of just, ideal weather. And, they did all their normal checks, as you always do. Everything was go. The early part of the launch was fine. A few minutes into the launch, especially as they're entering that second stage, they did experience anomaly. And if people were watching a replay of the video recorder, the video freezes out. And then a minute later, you kind of hear the critical parts. And surprisingly, the critical part is, oh, it didn't blow up. That doesn't really happen as much as you think. It's, oh, we're losing speed. As soon as you start to lose speed, you don't have extra fuel, the energy you need, the escape velocity, all of that stuff just dramatically changes. And you're talking about fractions of a second that if it doesn't go right, you don't reach orbit. And that's eventually what we saw, and it unfortunately came back to Earth not in the way everyone wanted.
And ROCKETLABS is an interesting one for us here in Australia because they're launching from a launch complex in New Zealand. So it's really cool to have New Zealand commentators counting down to launch.
That's right, especially when you get to 6. Sorry to all of our Kiwi friends. I have an American accent. We can't throw stones. But this sort of thing is, just 3 as he said, 3 weekends ago now, they had their successful launch. And in fact, one of the satellites built here in Canberra between 2 groups, including our group where I work up at Mount Stromlo Observatory, was on that rocket and was completely successful. And these things happen. And even, obviously the space shuttle had their 2 terrible disasters, but rockets have accidents. And it's not that it's a short-sighted part of the program, a mistake, anything you missed. These things happen. And yes, you've missed it, or it's a mistake, or something broke. But the same reason we take our cars to mechanic or airplanes get routine service, these things are complex machines, and it literally is rocket science. And it doesn't go according to plan. As you said, this was the 13th launch, and they've had just a huge run of successful ones. So it's always unfortunate to see, especially since last launch they had was delayed from an April window because of the coronavirus shutdown. And so they were, really on track, really moving it and trying to play a bit of catch up. And again, not to say that they were rushing it, they weren't, but it's a hard job.
Well, absolutely. And there were 7 payloads on board this one. They were going to be sent to separate destinations in low Earth orbit, with 6 out of the 7 serving as Earth observation satellites. So ROCKETLABS had christened the mission PIX, or it didn't happen. Unfortunately, it didn't happen.
That's right. And we got pics of it not happening, which was, the unfortunate thing.
I don't think they're going to use that ever again.
No, I think, that's kind of probably a doomed, ill-fated idea. Look, it's, again, one of those things that it is unfortunate. We've talked about the litany of failures that SpaceX has had in their new system and their, pressuring of their tanks and blowing up. It's hard. It takes a lot of time. And even when you think you have it right, little hiccups or snafus happen. And it's a very unfortunate thing for the people who had their satellite payloads on the rock. They lost it. I would say here, one of the things that probably isn't realized is Rocket Labs designed a small rocket on purpose to take small payloads, a few of them. So kind of like a puddle jumper plane, quicker ways into space. So, you take less, but it's cheaper and you could do it more often. And in some ways, if we want to look at a positive here, that has become a positive. If this was an Atlas V or a Falcon Heavy and it had, a huge payload or 60 satellites. Imagine this was a Starlink launch with 60 satellites and all of those were lost. The effects of the disaster, the accident are, dramatically more expensive and, far reaching. The fact that there was only 7 satellites launched instead of say 60 or 50 or, $2-3 billion satellites, something like that, limited the scope of the disaster, in some way showed the beauty of this system, that if something does go wrong, you're not talking, you're limiting the damage. And again, you don't want to plan for this. You don't want to think about it. That's not why you do it. But it just goes to show that even though the impacts to these groups who built these satellites obviously is far reaching and important and a big setback, the disaster isn't quite like what we'd have in the past. And it just shows the way that this new model is changing for the better space access.
Well, a new Electron rocket is being built every 18 days, and Rocket Lab was aiming to conduct monthly launches throughout the remainder of this year and into next, including the first launch from Launch Complex 2 at Wallops Flight's facility in Virginia, and the launch of a NASA spacecraft to almost a halo orbit around the moon using these Electron rockets and Photon satellite bus. So there's plenty of stuff that they're working on, and as you're saying, all these smaller satellites, that fast and rapid access to space, which is something that's starting to become a thing these days. It's more important to get lots of little things up than a few big things. So this launch, or this failure to launch, is going to maybe hurt those plans a little.
That's right. You want a lot more, as you said, you want that faster to access. So once your satellite is ready, you don't want to launch for a ride in 3 months. You want to be able to say, hey, it's like travel, right? You're planning a holiday or going somewhere. If the flight only happens every week or every month, you kind of are in a lull of waiting. But, having those daily options or multiple daily options allows you flexibility. And when you're ready, you're ready. Same with satellites. The more abilities to get them up there, when you're ready, you're ready. You can get where you want. And as you said, quicker. Obviously, this will delay the whole production and launch system. They will do, a full investigation with the authorities, both in New Zealand and the U.S., because they also are incorporated in the U.S., as you said, to make sure they're all safe and ready to go. And it also just shows a subtle thing. The reason rockets are launched partially from where they are is when you have these accidents, which if they're going to happen early relative in the launch. If something happens, they crash down and land in the ocean and not over land. So if this would have been launched, say, in Western Australia, on the other side of our continent, and did the same thing, it would have likely came down over an inhabited or at least a land area, something you don't want. So doing it over the ocean does have that, that safety thing. So it's a really all-encompassing way of why and how these things are chosen. But hopefully they figure out the problem, they solve it, and they're on launch pad soon.
Well, there we go. Another week of Talkin Science live and uncut flies by. Thanks so much for your company, either live or on delay. Don't forget, on our next edition of a Trekzone Conversation, episode number 405, Aussie Space Month continues. We're going to be joined by the chief engineer from Human Aerospace. They're designing the next generation of spacesuit. And then after that, we'll be joined by Dr. Brad Tucker who'll be talking about all the potential launch sites here in Australia. We're uniquely positioned where we are on the globe for potential rocket launches, either our own or supporting other missions as well, much like New Zealand is supporting ROCKETLABS' launches. Which is very, very cool. Aussie Space Month, all July here on Trekzone in the year of 2020, the hellish year of 2020 that it is. August is looking pretty cool as well. I'm already lining that up. We're going to be supporting Guide Dogs Australia's PAWGUST, walking for 30 minutes a day, every day on the month of August. That's about 12 hours, I think it is. For 14 hours, something like that. It's going to be absolutely crazy. About 2 kilometres a day. We'll have live updates on that one throughout the month of August. So I'm looking forward to that one. That's a great cause, supporting the Guide Dogs Association. And of course, Dr. Brad Tucker back on Tuesday for another edition of Talkin Science. It's jam-packed. Trekzone, Australia's unofficial home of Star Trek, now more than Trek. We're producing 6 podcasts a week. I don't know any other Star Trek podcast or sci-fi podcast or science and space news podcast doing that much content, 6 shows a week, which is a big effort, but seeing everyone support the channel is absolutely fantastic. Don't forget to like, follow and subscribe to Trekzone all over social media. Like this video as well. Help me get those warm and fuzzy feelings on the inside. That'd be absolutely fantastic. And the biggest thing that you could do for me, in fact, out of everything, is share us with your friends. And tell your friends about us if they don't know about us. We want to spread the word. We want to spread the love of Trekzone and really start getting out there and building our audience. That would be absolutely fantastic. Now's the time to do it. People can see fresh content 6 days a week from Trekzone. Get a sample for what we're doing and see whether you like us. And if you do like us, well, like, follow and subscribe. We're on Twitter, YouTube, Facebook, Instagram, and of course Tumblr. Tumblr, yeah, we are there. It's a unique platform. In my mind, but we are there. We are posting on Tumblr, so look out for us. Trekzone.org, wherever you want to find us, and of course podcasting as well in your favourite podcasting app. Just search for Trekzone or a Trekzone Conversation. You'll find us. Subscribe and leave that 5-star review, or a 4-star review if you want to. And of course, Dr. Brad Tucker on Facebook, Dr. Brad Tucker. And Twitter, btucker22. Alrighty, well, that's the socials done. That's the call-outs. That's the call to actions, if you will. Done and dusted. Talkin Science live and uncut. Done for another week as well. I'm Matt Miller at Trekzone HQ. Thanks very much for watching. We'll catch you again soon.